Alright, welcome to our first video on the applications of derivatives. And this is going to be on velocity and other rates of change. We'll spend a long time on this because derivatives are all about change. And why would there be calculus if there weren't applications of calculus? So basically what I want to talk about first is we've already seen the instantaneous rate of change is the same as the slope of the tangent line, and thus the derivative at that point. Unless we use the phrase average rate of change, we will assume from now on that in calculus the phrase rate of change refers to instantaneous rate of change. In other words, if I just ask what's the rate of change at 2, you can assume I mean instantaneous. If I say what's the average rate of change, then you know I mean average rate of change. So let's come down here. The length of a rectangle is given by 2t plus 1, and its height is the square root of t, where t is time in seconds, and the dimensions are in centimeters. Find the rate of change of the area with respect to time and indicate the units of measure for this rate. So if I want the rate of change of the area with respect to time, the area of a rectangle is length times width. So my area is 2t to the 3/2 plus t to the 1/2, right? Well, if I want to find the rate of change of area with respect to time, I want to find what's called the a dt. I want the derivative of a with respect to t, and that's going to be the derivative of this. So that's just going to be 3t to the 1/2 plus 1/2 t to the negative 1/2. What would the units of measure be for this weight? Well, we're talking about area with respect to time, so this would be measured in area units, which in this case would be square centimeters, and time units, which is seconds. All right? So there you go.
I want that, Mommy.
Now, if we want to talk about rectilinear motion is motion along a line. It's what you're used to. Position, velocity, acceleration. So there's a couple different vocabulary terms that I really need to make sure you know the difference between. Our first vocab term is going to be displacement, and that's our net change in position. Displacement can be positive or negative. If I move forward, it's positive. If I move backward, it's negative. The other thing you need to know about is average velocity. Average velocity is the net change in position divided by the total change in time. Okay. Your instantaneous velocity is your instantaneous rate of change. It's the derivative of the position function. So unless we use the term average velocity, we can always assume that the word just velocity refers to instantaneous velocity. Positive velocity indicates movement in the positive direction, which is right and up. Negative velocity means left or down. Speed. Speed is the absolute value of velocity. Speed is non-negative. It can be 0, it can be positive, it cannot be negative. And last but not least, acceleration is your instantaneous rate of change of velocity, implying that acceleration is the derivative of velocity. Since it's the derivative of the velocity, it's the second derivative of position. So what I'm going to do is off to the side here, I'm going to put some notations for each of these. So your displacement is your net change in position. So position we also often call x of t. So displacement would be x of t2 minus x of t1. Okay. Average velocity is your net change in position over total change in time. So I'm just going to write this one as x of t2 minus x of t1 over t2 minus t1. Instantaneous velocity is your velocity. It's your derivative. So this is just going to be x prime of t. Speed is the absolute value of velocity, so it's the absolute value of x prime. And acceleration would be x double prime of t. Oftentimes what you'll see is you'll see instantaneous velocity written as v of t, and we're completely fine with that. And you'll see x double prime written as a of t, and we are okay with that. All right, so Bugs Bunny has been captured by Yosemite Sam and is forced to walk the plank. Instead of waiting for Yosemite Sam to finish cutting the board from underneath him, Bugs decides to just jump. So here's Yosemite, he's trying to saw it off, and Bugs says, you know what, I'm not waiting for you, I'm just jumping off. Bugs' position h is given by h of t equals this, where h is measured in feet, and t is measured in seconds. Okay, so basically what you have to do from here is you have to interpret what they're asking, and just do what you're supposed to do with it. So, what we want to do here, when will Bugs hit the ground? Well, hitting the ground is a height thing, and hitting the ground means you don't have any height, your height is 0. So, when will Bugs hit the ground? That's going to be when our height is 0. So when is 16t squared, 16t 320? When does that equal 0? Okay, so when we're doing stuff like this with numbers this large, you're going to be able to use your calculator. So I'm going to pull mine up here. So I am going to go into y equals here, negative 16t squared plus 16t plus 320. And I'm going to change my window to go from like 0 to, I don't know, 15. Because remember, this is time, and it's time to hit the ground. I don't think Bugs is going to be falling for much more than 15 seconds. And since I'm looking for when it equals 0, y min and max of negative 1 to 1 is fine. I hit graph. I look for when it, there we go. Let's see. Second calc. Come on. Second calc. 0. That looks like it's at 1, 2, 3, 4, 5. So I'm going to say left bound is 3. Right bound is 7. And look at that. It's exactly 5. Bugs will hit the ground at t equals 5 seconds. What is Bugs' velocity at the time of impact? Well, let's see. Velocity is the instantaneous rate of change in position. Velocity is the derivative of position. So his position is his height. So his velocity is going to be h prime or v of t. I don't care if you call it v. I completely understand that. So I then am going to change this to negative 32t plus 16. And if I want the velocity at the time of impact, he impacts at 5 seconds, so it's going to be negative 32 times 5 plus 16. And if I come over here, negative 32 times 5 plus 16. Negative 144. And what are my units of measure? Well, my units of measure are, let's see, v is a velocity, and it's feet per second. What is Bugs' speed? Speed is simply the velocity's absolute value. So if velocity is negative 144 feet per second, his speed is a regular 144 feet per second. Now, before I move on, I want to show you a calculator trick, so please pay attention. What we just did there is we took the derivative of this function at 5. Your calculator actually knows how to do that, and it does it very, very well. Now, some of this calculator notation may be different for some of you, so if your calculator doesn't look like this, come and talk to me at class, and I can show you the syntax on your calculator specifically. But anyways, if you want to take the derivative in your calculator of something, the first thing you want to do is put that something into y1, which I already have, and then you want to go to math, and then number 8 says n deriv. So math 8, and it shows this right here. I want to take the derivative with respect to x, so I typed an x there, of what's in y1, and I want to do so at x equals 5. So this notation means take the derivative with respect to x of the y1 equation, do it at x equals 5, there's your derivative. There's that negative 144. It did it for us. It's fantastic. Okay? So, little tricks on your calculator. You can do it right there. The other place you can do it is you can actually even do it on the graph. If you look at this graph right here, you can do second calc dy dx number 6, and then just type in 5. And it will again give you negative 144. I don't like that so much because if it's not actually in the window, it won't do it for you. So the home screen, I think, is better. But in any case, you can do it on the graph. So back to here. Find Bugs' acceleration as a function of time. What are the units for this value? So acceleration is the second derivative, which would be the derivative of velocity. So acceleration is the derivative of velocity, which is negative 32. That's it. There's no t's. So my acceleration is a constant at negative 32. And this is going to be feet per second per second, because each time I take a derivative, I add a per second to it. So derivative number 1 became feet per second. Derivative number 2, feet per second, which you're probably used to seeing as feet per second squared if you've taken physics. Okay? All right. So this one, let's go through it together. We've got Marvin the Martian over here. He has that kind of voice. He's trying to blow up Earth because it interferes with his view of Venus. He lands on the moon. Bugs Bunny, as always, interferes with his plan. They chase. Marvin fires a warning shot straight up in the air with his Acme disintegration pistol. You can imagine it's going to fall back down and hit him in the head. Find the height. Well, the height in feet after t seconds is given by this. Okay, notice the change in our coefficient here because we're on the moon, there's less gravity. Find the velocity and acceleration functions of time. What's the meaning of the acceleration function? Okay, so velocity here. Velocity is s prime of t, which I'm going to call v of t, is the derivative of this, so negative 2.66 times 2. And negative 2.66 times 2 is negative 5.32. And that's going to be negative 5.32t plus 135. And our acceleration function, which again is the second derivative of position, also the first derivative of velocity. My acceleration function is the derivative of that, which is negative 5.32. What's the meaning of acceleration? When you're talking about something like this is gravity. Acceleration isn't always gravity, but when you're talking about something that's going straight up or straight down or both, your acceleration function is going to be your acceleration due to gravity. Okay. All right, so how long will it take Marvin the Martian shot to reach its maximum height? Now, there's a couple different ways to do this. I'm going to give you the quickest way, I think. If you want something to reach maximum height, you need to think about velocity. You need to think about when you throw something. So if you throw something, it goes up and then it comes back down. Well, when it's going up, its velocity is positive because it's moving in an upward direction. And when it's coming down, its velocity is negative. Therefore, what's its velocity right there? Well, it goes from positive velocity to negative velocity. So at the top, it's got to have 0, right? To go from a positive to negative, you'd have to pass through 0 because of the intermediate value theorem. So if I want to know where his maximum height occurs, I can figure out when the velocity equals 0 and say, all right, well, when does negative 5.32t plus 135, when does that equal 0? Well, that's going to be at 135 divided by 5.32. And that is 25.3759. Remember, we need 3 decimal places, so we'll do 25.376. And that's how long it takes for it to reach the maximum height. Now, how do I know that's the maximum and not the minimum? Because of the context of the problem. He's shooting the warning shot in the air and then it comes back down. It's not going to make some kind of sine curve in the air. That's not happening. It only has a maximum height. It doesn't really have a minimum height. And then what is the maximum height for Marvin shot? Well, for that, if I want to know the maximum height, I should plug this back into the height equation. So I need h of 25.376 seconds. And so if I want h of 25.376, I want h of that answer right there. So I'm going to take that and I'm just going to do negative 2.66 times the answer squared plus 135 times the answer plus 3. And 1715.876. Okie doke. Now, one thing that you want to be careful of just for future reference here is all of your answers need to be correct to 3 decimal places. You can't use the 3 decimal places of one answer and only use those to get another one because you might be off. So if I did negative 2.66 times 25.376, there we go, squared, and then plus 135 times 25.376 plus 3, I get 1715.875. I'm actually okay with that one. That's weird. But basically what I was trying to get at there that you didn't see is if this changed to 1715.873, and the answer is supposed to be 0.876, you're going to get a point off because you're supposed to use your calculator to the best of your ability, which will allow you to get an accurate answer to 3 decimal places. So that's what you really need to do. So whenever you have an answer on the screen, use that second answer button or use the store button that I've showed you how to use, and that will get you the values to their exact one. Obviously, this wasn't a great example. I thought maybe it would work. It didn't, but hopefully you get the gist. Table 1. We've got rocket A has a positive velocity that's given here in this table. The velocity of the rocket is recorded for selected values, and they're shown in the table below. Find the average acceleration. Well, I didn't write down a formula for that, but what you need to think about as well, if average velocity is position over time, average acceleration would be velocity over time. All right? So if I want to find average acceleration, I just need to find the net change in velocity over time. And I want average acceleration over 80 seconds, so I need v of 80 minus v of 0 over 80 minus 0. So this is going to be 45/80ths is your average acceleration. Indicate units of measure. Well, velocity was feet per second, and then we have another second, so this is feet per second squared. Using the data, find an estimate for v prime of 35. All right, so v prime of 35 would be like the derivative of v at around 35. The derivative of v is like the slope of v. So if I want to find v prime of 35, I can find the slope between 30 and 40, because that's going to be a decent estimate for the slope at 35. And a good example of that is, let's say our velocity curve looks something like that. If my velocity at 30 here is there, and my velocity at 40 is there, the slope at 35 would be something that looks like this. The slope between 30 and 40 is pretty close to that, right? They look relatively parallel, and that's going to happen a lot. So if you ever want to find an estimate for a derivative, what you really need to think about is the fact that that's really just slope. And so you find the slope, you do what we call hug the point. You find the slope between a point a little bit above and a little bit below. So v prime of 35 is going to be v of 40 minus v of 30 over 40 minus 30, which is going to be 35 minus 29 over 10, which is going to be 6/10. And this is an estimate for the rate of change of velocity, so this is going to be feet per second squared again. Okay, that's enough for one evening. We're going to talk a little bit more about this stuff tomorrow, and you'll do some more in class. Hopefully this audio sounds pretty good. I had to use a different headset. If it doesn't, I apologize. All right, so we need a joke. I don't have a great one for today. What do you call an alligator in a vest? An investigator. I know it's really not that funny. Have a great night. I'll try to think of a better joke for tomorrow.